So, now let us see what is the degrees of freedom and how it will decide how much energy a given molecule can carry. So, with degrees of freedom we mean the number of quadratic terms which comes or which is used to express the total energy possessed by a gas molecule. So, in terms here you can use another word also. With degrees of freedom we mean the number of energy terms, kinetic energy terms. So, you see this is quadratic term I have written, that can be also replaced by kinetic energy terms. So, this is the general term used in textbooks, kinetic energy terms. I have used quadratic terms because sometimes another energy terms are also used. So, this point has to be mentioned. So, if you are writing general notes, you write kinetic energy terms. If it is general, then quadratic terms. So, I will explain when I will take an example. So, the number of degrees of freedom, we mean the number of quadratic terms which comes or which is used to express the total energy possessed by a gas molecule. Let us take an example. Example of monoatomic gas. Monoatomic gas. So, let us take an example of monoatomic gas. So, the energy possessed by a monoatomic gas molecule, the energy possessed by a monoatomic gas molecule is given by we will write E as half mvx square plus half mvy square plus half mvz square. So, here we have three terms. These are quadratic terms which are used to express the total energy. So, you see here this is x axis, y axis and z axis, and if I have a molecule with velocity c, I can write this as Vx, one component Vy, one component and Vz. So, the total energy expression contains these three terms. So, we call each these quadratic energy terms as a degree of freedom. So, thus a monoatomic gas molecule has three translational degrees of freedom. So, degrees of freedom means all the individual kinetic energy terms which are used to express E. These kinetic energy terms can be assumed to be some pockets of energy that I will explain later. So, first only let us see what are the degrees of freedom for different gases. So, we have three translational degree of freedom for a monoatomic gas. That means a monoatomic gas has freedom to acquire Vx separately, Vy separately and Vz separately. And so, the total velocity, the total energy of such a molecule can be handled by handling the individual term. This is what we mean by degree of freedom. Three pockets, three areas where we can give energy into the system. Now, let us see the degrees of freedom of a diatomic gas molecule. So, suppose I have a diatomic gas molecule, and suppose diatomic means it is something dumbbell type. This is AA type or AB type. AA type means oxygen, nitrogen, chlorine. This is HCl gas type, AB type, AA type. So, we have different small, big, identical like that. So, we have different type of diatomic gas molecules also. The expression for the total energy, that is the kinetic energy of a diatomic gas molecule is given by E is equal to half total mass. This is the mass of each molecule, each atoms to form a molecule, half mvx square, half mvy square plus half mvz square. So, these are 3 translational plus half suppose ix wx square plus half iy wy square plus 2 rotational. We have taken 3 translational and 2 rotational, and I have neglected the third one. Let us see why I have neglected. So, suppose this is x axis, y axis and z axis. I have neglected the z term. Suppose the molecule is like this. So, it is rotating about this axis. So, when it is, these are the atoms to form a molecule. So, it rotates about z axis. I can neglect the moment of inertia here. So, the energy associated with this motion is comparatively less. So, I have neglected this term, third term. Next, if it is x, this is y and this is z. Suppose this molecule is here and it rotates about this axis, x axis, that means along this. So, you see it has a large moment of inertia because more mass is distributed from the rotation axis. You see x axis, x dash axis is the rotation axis. So, I have assumed this term. Similarly, this is your x axis, y and z, and if it rotates in this plane like this, so that the rotation is along y axis. So, still the along y dash axis, its moment of inertia is large compared to this. So, here I can neglect this moment of inertia. So, energy associated with this can be neglected. So, we have these are 2 rotational degrees of freedom, these 2, and this means we have again a molecule like this which can move in this direction, this can move along this direction, and this can move along this direction also. So, it has along y direction, along x direction, along z direction, velocity I will call this Vy, this is Vz, this is Vx. That means it has 3 translational kinetic energy, 2 rotational degrees of freedom. So, total degrees of freedom for a diatomic gas molecule is equal to 5. This is the 5 degrees of freedom. Here it is assumed that this gas molecule is not having vibration. At higher temperatures, vibration has to be also accounted, but at lower temperature vibration is not taken. So, this important point that this is the diatomic gas molecule without vibration, means this will happen only at low temperatures. So, now diatomic gas molecule, so vibration type. So, vibration also we will taken, that is vibration is included. So, let us see, at higher temperatures, the molecules possess vibrational energy. Thus, the total energy expression becomes, for a diatomic becomes, E is equal to half mvx square, half mvy square, half mvz square. So, we have 3 translational degrees of freedom plus half Ix omega square plus half Iy omega square, 2 rotational degrees of freedom. I have neglected the third one, plus 2 vibrational. You see, you recall, suppose we have a mass m1 and then another mass m2 connected by a spring. Suppose this is a spring of spring constant k, then we can replace this by a spring of spring constant k and with a single mass called reduced mass, and the total energy then becomes mu v relative square plus half k x square, where relative velocity of these two. So, the total energy due to vibration will be something half mu v relative whole square plus half k x square. So, you see, that is why you see this term, this is not a kinetic energy term. All the terms are kinetic energy, but this is potential energy term. So, why? So, that is why in the very beginning the definition I wrote the quadratic term. I did not write that kinetic energy term, because this is not a kinetic energy term, this is a quadratic term, but it accounts for a degree of freedom. So, we have two vibrational degrees of freedom. So, thus diatomic gas molecule will have 5 without vibration, and will have 3 plus 2 5 plus 2 7 with vibration. So, this is the degrees of freedom of a diatomic gas molecule. Now, let us come to polyatomic gas molecule. Okay. So, now let us come to polyatomic gas molecule bracket non-linear type. So, again we are going to use E as half mvx square plus half mvy square plus half mvz square. These are the 3 translational plus half Ix omega x square plus half Iy omega y square plus half Iz omega z square. Here, since it is non-linear type, so I have to use the third one. If it is again linear type molecule, I won't use the third term, even if it is polyatomic. So, 3 rotational, and depending on whether temperature is high or not, we will see half mu v relative square plus half k x square, 2 vibrational. So, we have to remember the vibrational states are excited at higher temperature, not at lower temperature. So, total degrees of polyatomic gas molecule will have 3 plus 3 6. So, 6 6 under normal circumstances, so no vibration, and 6 plus 2 8 with vibration. So, this is how the degrees of freedom for a gas molecule is defined. Now, let us see how these degrees of freedom provide different ways of storing energy for a gas molecule.